Welcome back. Physics builds models. Chemistry builds structures. Biology builds evolutions. 3 ladders, 1 way of thinking. And today, we drop that thinking straight onto a real exam idea, showing how the same ladder mindset turns a spectroscopic analysis into a clean, logical reconstruction of an unknown molecule using mass spectrometry, to the power of 1 h NMR, and to the power of 1 cubed c NMR. Today's focus: spectroscope analysis from the 2025 VCE Chemistry exam, reading the base peak at Z59, decoding chlorine isotope patterns at 108 and 110, identifying the Z95 fragment, extracting hydrogen environments from the 1:2:6 integration ratio, using carbon-1,3 symmetry to constrain the skeleton, and finally assembling and naming the structure that fits all spectral evidence. Identify the Z of the base peak. 1 mark. In mass spectrometry, the spectrum is plotted with the mass-to-charge ratio on the horizontal axis and the relative intensity on the vertical axis. The base peak, by definition, the base peak is the tallest peak on the spectrum, representing the most abundant stable fragment ion produced during ionization. The scale, to make data comparison straightforward, the intensity of this most abundant fragment is arbitrarily assigned a value of 100%. All other peaks are scaled relative to it. Looking directly at the provided graph, the highest line hits exactly 100 on the vertical axis. Dropping straight down to the horizontal axis reveals that this line sits precisely 1 unit to the left of the 60 mark, making it 59. Reviewing the question stem. To see why this question caught 59% of the state off guard, we have to look closely at the clues VCAA explicitly provided in the question stem. The only stable isotope of oxygen is 16O. The 2 naturally occurring, stable isotopes of chlorine are 35Cl and 37Cl. Whenever an exam question explicitly lists specific isotopes, it is a massive red flag. The examiners are signaling that you must think about individual, discrete molecules, not the weighted atomic averages found on the periodic table. The trap: whole mass numbers versus decimal molar mass. When students see a chemistry question involving molecular mass, their instinct is to calculate the relative molecular mass. If you do that here, using chlorine's average mass of 35.5, you get a total mass of 108.5 g per mol. Students then write on their exam papers, all isomers show a peak at 108, because they have the same molecular mass of 108.5. This is an automatic 0-mark answer. Why? Because a mass spectrometer does not measure average molar masses, and a decimal peak, at 108.5, does not exist on this spectrum. A mass spectrometer weighs individual ions one by one using the whole mass numbers of specific atoms, 16O equals 16, 35Cl equals 35, 37Cl equals 37. Understanding the parent ion, molecular ion, peaks. The largest intact fragment of compound X, before it breaks apart in the ionization chamber, is the unbroken molecule itself, known as the parent ion, or molecular ion, M reciprocal plus. Because structural isomers share the exact same molecular formula, they contain the exact same pool of atoms. When you inject a sample of any isomer into the machine, the individual molecules will split into 2 distinct isotopic populations based on which chlorine atom they happen to contain. The light parent ion, molecules that contain the 35Cl isotope, will have an exact whole mass number total that hits the detector precisely at Z equals 108. The heavy parent ion, molecules that contain the 37Cl isotope, will have an exact whole mass number total that hits the detector precisely at m as z equals 110. The final verdict. Changing the structure of an isomer changes how the bonds are arranged, but it does not change the molecular formula or the presence of the 35Cl isotope. Therefore, every single possible structural isomer of compound X will always contain a large population of molecules made with 35Cl, ensuring that a parent ion peak at m as z equals 108 appears consistently across every single spectrum. Identify the formula of the species responsible for the peak at m as z equals 95. 1 mark. This is a textbook trap question, and it's the exact reason why 90% of students walked away with 0 marks. The logic ladder for identifying peak 95. Identify the isotope, Cl. The peak at m as z equals 95 is roughly 1/3 the intensity of the peak at m as z equals 93. This 1:3 ratio is the classic signature of chlorine, 37Cl, 35Cl 1:3, confirming that the fragment at m as z equals 95 contains a 37Cl atom. Determine the fragment lost. The parent ion containing 37Cl has a mass of 110. The mass lost to form this fragment is 110/95 is equal to 15. A mass loss of 15 corresponds to a CH3 methyl group, proving that the oxygen atom, 16, was not lost and remains inside the fragment. Deduce the hydrocarbon backbone. Subtracting the known heteroatoms from the fragment mass leaves the hydrocarbon portion. 95-37, Cl, 16, O, equals 42. 4 carbons, 48 is equal to 12 times 4 2 heavy, 48 greater than 42. 2 carbons, 24 is equal to 12 times 2 requires 18 hydrogens, 42-24 is equal to 18, which is chemically impossible for a 2-carbon chain. Max is 6 is equal to 2 times number of carbon plus 2 equals 2 times 2 plus 2. 3 carbons, 36 is equal to 12 times 2 leaves exactly 6 hydrogens, 42-36 is equal to 6, which perfectly fits a stable structure, C3H6. Assemble the final formula. Combining C3H6, 37Cl, and O, and remembering that a mass spec only detects positive ions, gives the final 1-mark answer. C3H637 Clo with a plus on top. The high-resolution 1H NMR spectrum for compound X is shown below. Data obtained from the 1H NMR spectrum for compound X is shown in the table below. Referring to the 1H NMR spectrum and the table above, deduce 3 things about the structure of compound X, 3 marks. This is a textbook trap question, the exact one where 46% of students walked away with 0 marks, and only 5% scored full points. The trap? Relying on chemical shifts. For 1H NMR, chemical shifts are unreliable and should only be used for final confirmation. The real keys to unlocking this spectrum are the number of environments, the splitting patterns, and the integration ratios. Let's look at the data. To secure 3 marks, each deduction must follow A, from data to meaning structure, pick any 3. Deduction 1, number of environments. There are 3 distinct peaks on the spectrum, which means compound X contains exactly 3 unique hydrogen environments. Deduction 2, proton ratio. The relative peak areas of 16.7, 33.3, 100 simplify to a 1:2:6 ratio. Given our molecular formula has 6 hydrogens in this fragment block, This translates to a total of 9 hydrogens in the molecule, 1H, 2H, 6H. Deduction 3, Symmetry. The largest peak represents a 6H environment, which deduces the presence of 2 identical, symmetrical CH3 methyl groups in the molecule. Deduction 4, Splitting in neighboring. Every single peak shown in the spectrum is a singlet, unsplit single line. According to the N+1 rule, this deduces that none of the hydrogen environments have any adjacent hydrogens on neighboring carbons. Warning sign # the chemical shift trap. Many students tried to use the chemical shift values 2.8, 2.5, 1.3 ppm to pinpoint the functional groups. The examiner explicitly stated that no marks were awarded for using chemical shifts, as they were unreliable, ambiguous for this specific unknown compound. Students must learn to rely on peak count, splitting, and area integration instead. Warning sign # the vague description error. Students frequently wrote down structures like it has a methyl group, or it has a carbon chain, without stating how they knew it. To get the mark, the observation must precede the deduction, such as the relative peak area ratio is 1 to 2 to 6, showing a total of 9 hydrogens. When solving any NMR spectrum, remember the big 3. Count the peaks, check the splitting, and find the ratio. Leave chemical shifts until the very end just to double-check your work. Just like the 1H NMR question, students are failing. 19% got full marks, because they are obsessed with chemical shifts rather than analyzing the symmetry and count of the signals in the spectrum. The symmetry and count logic ladder. To get the 2 marks, students must move away from guessing functional groups and focus on these 2 hard facts. Fact 1. Count the environments. The 13C NMR spectrum displays 3 distinct peaks. This observation proves that compound X contains exactly 3 unique carbon environments. Fact 2. Deduce the symmetry. Since the molecular formula contains 4 carbons, but only 3 signals appear in the spectrum, there must be molecular symmetry present. Specifically, 2 of the 4 carbons must be chemically equivalent, meaning they occupy identical positions in the molecule and produce overlapping signals. Peak count always trumps chemical shift. 13C NMR is the symmetry detective. Stop looking at the x-axis, ppm, first. The most important information in a 13C NMR spectrum is hidden in the number of peaks. If the number of signals is less than the total number of carbons in your formula, you have just found your strongest evidence for molecular symmetry. A staggering 85% of students scored 0 on this drawing question. Not because their chemistry was wrong, but because they ignored one critical keyword, skeletal. If you write a single C or H for your methyl groups in a final skeletal diagram, VCAA gives you a straight 0. But don't panic. Here is my pro tip: always sketch the carbon skeleton first, and then translate it into the final pristine skeletal diagram. Let's piece the puzzle together step by step. Left-pointing magnifying glass. Step 1, mass spec, the molecular formula. First, let's look at the mass spec. Part C showed that the fragment at Z equals 95 is C3H637 Clo top plus, while the molecular ion peak is at Z equals 110. The exact difference between 110 and 95 is 15, which perfectly fits a CH3 methyl group. This mathematically proves that our total molecular formula is C4H9 Clo. Left-pointing magnifying glass. Step 2, 13C NMR, the symmetry proof. Second, let's cross-reference the 3C NMR. The spectrum displays only 3 peaks, but we know we have 4 carbons in total. This mismatch is a dead giveaway for molecular symmetry. 2 of the carbons must share the exact same chemical environment. Left-pointing magnifying glass step 3, 1H NMR, the microassembly. Finally, we bring in the 1H NMR to freeze the structure. The spectrum gives us 3 proton signals with an integration ratio of 6:1. The 6H signal must come from 2 equivalent CH3 groups, confirming our symmetry. The 2H signal comes from a CH2 group. The 1H signal comes from the OH group. Now, look at the splitting. All 3 peaks are singlets. This means none of these groups have any neighboring hydrogens on adjacent carbons. How is this possible? Only if the adjacent central carbon is a quaternary carbon, a carbon with 0 hydrogens attached. Step 4, the final construction, the draft to skeletal method. To satisfy the tetravalency of carbon, we must bond the 2 CH3 groups and the 1 CH2 group directly to this central quaternary carbon. The remaining OH and Cl groups will fill the rest of the positions. This gives us 2 possible isomers for compound X, 1-chloro, 2-methylpropane 2-ol or 2-chloro, 2-methylpropane 1-ol. For the final 1 mark, wipe away all the CS and HS bonded to carbons, and convert it into the perfect skeletal format. Now, let's talk about the naming rules for Part 2. Your IUPAC name must absolutely match whatever structure you drew in Part I. The golden rule here is functional group priority. The OH group is the king of this molecule, completely outranking the chlorine atom. Let's look at the 2 paths you could have taken. If your OH is in the middle on that quaternary carbon, it sits at position 2. To keep your numbers as low as possible, you count from the side closest to the chlorine, giving you 1-chloro, 2-methylpropane 2-ol. If your Cl is in the middle instead, the OH is forced to the edge. Since OH is your principal group, that terminal carbon must be position 1. That sets the chlorine at position 2, giving you 2-chloro, 2-methylpropane 1-ol. The real tragedy of this question. It's a double jeopardy trap. If you got Part I wrong, you are dead in the water here. That's exactly why 73% of the state failed this question. You have to get the skeleton right to get the name right. Now, let's go beyond VCE. Both isomers perfectly satisfy the NMR spectra, so how do we pinpoint the exact identity of compound X? The smoking gun is hidden right in the mass spec, specifically, the base peak at M(Z = 59. Look closely at M(Z = 61. Do you see a peak that is 1/3 the height of the 59 peak? No. It's completely missing. This absolutely rules out chlorine from being inside this major fragment. So, what broke off? In organic mass spectrometry, the carbon-carbon bond adjacent to a heteroatom, like the oxygen or chlorine, is highly prone to what we call alpha cleavage. The molecule snaps right there, throwing away a neutral .CH2Cl radical because the neighboring heteroatom acts as a powerful stabilizing anchor for the remaining positive charge. Let's do the math. The molecular ion for the 35Cl isotope is at 108. If you subtract our base peak of 59, you get exactly 49, which is the precise molar mass of a .CH2Cl fragment. In fact, if you look down the spectrum, you will find a pair of smaller peaks at M(Z = 49 and 51. Why are they so weak? Because when that fragile bond snaps, The vast majority of these chlorine fragments fly off as uncharged, neutral radicals, .CH2Cl, which are completely invisible to the MS detector. Only a tiny fraction of them carry the positive charge. But even though they are weak, they still show that classic 3:1 chlorine isotope signature, 51 being 1/3 the height of 49, proving beyond doubt that chlorine is right there. This settles the debate once and for all. Compound X is definitively 1-chloro-2-methylpropane-2-ol. Chemistry is beautiful when the math just clicks. Mass spec gives the map. Base peak at M(Z) equals 59, with parent ions at M(Z) equals 108, 35 Cl, and 110, 37 Cl. Listed isotopes are a red flag. Use whole mass numbers for discrete molecules, never the averaged molar mass. The 3:1 chlorine isotope ratio pins the M(Z) equals 95 fragment, as is C3H637 Clo+. NMR cracks the structure, count 13 C peaks for symmetry, and read the 1H6:2:1 singlets to a quaternary center, not chemical shifts. Formula C4H9 Clo gives a skeletal diagram, named 1-chloro-2-methylpropane-2-ol, or 2-chloro-2-methylpropane-1-ol, draw skeletal, not letters. Beyond VCE, alpha cleavage loss of CH2Cl confirms the true compound X is 1-chloro-2-methylpropane-2-ol. At the end of every lesson, I want to leave you with one idea: learning becomes powerful when you climb the logic ladder. Physics moves from situations to models to equations. Chemistry builds from structure to property to reaction. Biology grows from variation to adaptation to survival. Different subjects, but the same underlying logic. When you learn to decode systems, build ladders, and construct logic, you don't just solve problems, you understand how they fit together. If you'd like to keep climbing this ladder with me, you can find more lessons, breakdowns, and reconstructions on my channel. Thanks for learning with me today.